What we're going to do here is try to do sentiment analysis. So this is going to be an example of a sequence to vector RNN problem, where we're taking the sequence of words in a user-written movie review, and we try to output a vector that's just a single binary value of whether or not that user liked the movie or not, whether they gave it a positive rating. So this is an example of doing sentiment classification using real user review data from IMDb. And since I used to run IMDb's engineering department, this is a little bit too tempting for me not to do as an example here. Now, mind you, just to give credit where credit is due, this is drawn heavily upon one of the examples that ships with Keras, the IMDb LSTM sample. I've sort of embellished on it a little bit here, but the idea is there, just to give credit where credit's due. And it does warm my heart, by the way, that they include the IMDb dataset as part of Keras for you to experiment with. So it's bringing back good memories for me. I enjoyed working there. Anyhow, this is another example of how we're going to use LSTM cells, long short-term memory cells, because again, when you're dealing with textual data, a sequence of words in a sentence, it doesn't necessarily matter where in the sentence that word appeared. You don't want the property of words toward the end of the sentence counting more toward your classification than words at the beginning of the sentence. In fact, often it's the other way around. So we're going to use an LSTM cell to try to counteract that effect that you see in normal RNNs where data becomes diluted over time, or as the sequence progresses in this example. So let's just dive in and see how it works. We'll start by importing all the stuff that we need from Keras. We're going to use a sequence, pre-processing module, sequential model, so we can embed different layers together. We're going to introduce a new embedding layer as part of our RNN in addition to the dense layer that we had before. We will import the LSTM module. And finally, we'll import the IMDb dataset. So let's go ahead and shift enter to do all of that and get Keras initialized. And that's done now. So now we can import our training and testing data. Like I said, Keras has a handy dandy IMDb dataset pre-installed. Oddly, it has 5,000 training reviews and 25,000 testing reviews, which seems backwards to me, but yeah, it is what it is. The one parameter you're seeing here for num words indicates how many unique words that you want to load into your training and testing dataset. So by saying num words equals 20,000, that means that I'm going to limit my data to the 20,000 most popular words in the data set. So if someone uses some really obscure word, it's not going to show up in our input data. Let's go ahead and load that up. And since it does have to do some thinking, it doesn't come back instantly, but pretty quick. Okay, we're in business here. Let's take a peek at what this data looks like. So let's take a look at the first instance of training data here. And what the heck? It's just a bunch of numbers. It doesn't look like a movie review to me. Well, you can be very thankful to the folks at Keras for doing this for you. So the thing is, when you're doing machine learning in general, usually models don't work with words, they work with numbers, right? So we need to convert these words to numbers somehow as a first step. And Keras has done all this pre-processing for you already. So, you know, the number 1 might correspond to the word the, or I actually have no idea what it corresponds to. But they've encoded each unique word between 0 and 20,000, because we said we wanted the 20,000 most popular words, to numbers. Okay, so it's kind of a bummer that we can't actually read these reviews and get sort of an intuitive meaning of what these reviews are saying, but it saves us a whole lot of work. And I've said before that often a lot of the work in machine learning is not so much building your models and tuning them, it's just processing and massaging your input data and making sure that your input data looks good to go. So even though this doesn't look like a movie review, it is a movie review. They've just replaced all of the words with unique numbers that represent each word. We can also take a look at the training data. So the classification of this particular review was 1, which just means that they liked it. So the only classifications are 0 and 1, which correspond to a negative or a positive sentiment for that review. Okay, so we have all of our input data converted already to numerical format. That's great. Now we just have to go ahead and set things up. Let's start by creating some vectors for input here. So we're going to break out our training and test data here. We're going to call sequence.pad sequences just to make sure that everything has a limit on them to 80 words. So the reason we're doing this is because, like we said, RNNs can blow up very quickly. You have to backpropagate through time. So we want to have an upper bound on how many time steps we need to backpropagate to. So by saying max len equals 80, that means we're only going to look at the first 80 words in each review and limit our analysis to that. So that is a way of truncating our backpropagation through time. It's sort of a low-tech way of doing it, but it's effective. Otherwise, we would be running this thing for days. Okay, so the only point here is to trim all of these reviews in both the training and the test data set to their first 80 words. which again have been converted to numbers for us already. Let's build up the model itself. Hey, we didn't actually run that, so let's go ahead and hit Shift-Enter on that block. Okay. Now we can build up the model itself, and for such a complicated neural network, I think it's pretty remarkable how few lines of codes are going on here. So let's talk through this. We'll start by creating a sequential model, meaning that we can just build up the topology of our network one step at a time here. So we'll start with some additional pre-processing. We're using what's called an embedding layer here, and all that does is convert our input data of words up to the first 80 words in a given review into dense vectors of some fixed size. So it's going to create a dense vector of a fixed size of 20,000 words and then funnel that into 128 hidden neurons inside my neural network. So that's all that embedding layer is doing. It's just taking that input textual data that's been encoded and converting that into a format that's suitable for input into my neural network. Then, with a single line of code, we build our recurrent neural network. So we just say add an LSTM, and we can go through the properties here. We're going to say we're going to have 128 recurrent neurons in that LSTM layer. And we can also specify dropout terms just in that same command here. So we can say that we want to do a dropout of 20%, and that's all there is to it. That one line of code sets up our LSTM neural network with 128 recurrent neurons and adds dropout phases of 20%, all in one step. Finally, we need to boil that down to a single output neuron with a sigmoid activation function because we're dealing with a binary classification problem, and that's it. So we've defined the topology of our network with just 4 lines of code, even though it's a very complicated recurrent neural network using LSTM cells and dropout phases, but Keras makes that all very easy to do. We then need to tell Keras how to optimize this neural network and how to train it. So we will use binary cross-entropy because this is ultimately a binary classification problem. Did the person like this movie or not? We'll use the atom optimizer this time, just because that's sort of the best of both worlds for optimizers. And then we can kick it off. So let's go ahead and run these 2 previous blocks. Shift-Enter. Shift-Enter. And at this point, you're ready to actually train your neural network. And let's just walk through what's going on here. It's very similar from the previous examples. In this case, we're going to use batch sizes of 32 reviews at once. We're going to run it over 15 training steps, or epochs, set a verbosity layer that's compatible with IPython notebooks, and provide the validation data for its use as well. Now, again, I'm not going to actually run this right now because it will take about an hour. Like I said, RNNs are hard. They take a lot of computing resources. And since all I'm doing is running this on my single CPU, I don't even have things configured to use my GPU or let alone a cluster of computers, this takes a long time. But I did run it earlier, and you can see the results here. So over 15 epochs, you can see that the accuracy that it was measuring on the training data was beginning to converge. Seems like after about 13 steps, it was getting about as good as it was going to get. And then furthermore, we can actually evaluate that model given the testing data set. So let's go ahead and call evaluate on that with our test data, again using 32 batches. And if we were to run that, we would see that we end up with an accuracy of 81% on our model here. Doesn't sound that impressive, but when you consider that all we're doing is looking at the first 80 words of each review and trying to figure out, just based on that beginning, whether or not a user liked the movie or not, that's not too bad. But again, step back and think about what we just made here. We've made a neural network that can essentially read English language reviews and determine some sort of meaning behind them. In this case, we've trained it how to take a sequence of words at the beginning of a movie review that some human wrote and classify that as a positive review or a negative review. So in a very real sense, we've at some level, at a very basic level, taught our computer how to read. How cool is that? And the amount of code that we wrote to do that was minimal, right? So it's kind of mind-blowing. It's really just a matter of knowing what technique to use to build your neural network, providing the appropriate training data, and then your neural network does the rest. It's really kind of spooky when you sit back and think about it. Anyway, cool stuff. So it's a great example of how powerful Keras can be, and a great example of an application of a recurrent neural network, not using the typical example of stock trading data or something like that, but instead for sentiment analysis, where we took a sequence of words and used that to create a binary classification of a sentiment based on that sequence. So fun stuff, RNNs and Keras.